Welcome back. Today we're going to look at a new topic, something we refer to as standard deviation. Now, standard deviation is a very useful tool. We use it to measure out how spread out the numbers are in a set of data. In other words, we're trying to find out how far the typical number is away from the mean as we observe a set of data. If the standard deviation is high, that might mean that the numbers are really spread out in comparison to one another. And if it's a really low value, that might mean that the numbers are all very close to one another in value. This is a very useful tool as we look to compare different sets of data to one another, and we'll take a look at some examples like that in just a minute. Again, it's defined as the average distance that each item is away from the mean of the data. So we would first off have to know what the mean is, and then we're going to find how far each number is from the mean and basically take the average of those numbers. Now there are some things that we'll have to do as we work with those in order to counter some things that might happen if we don't take these measures. But all in all, we're basically just averaging out how far each number is away from the mean. That said, let's look at the formula for standard deviation. And it's supposed to be down here. Let's see. There it is. We'll move it up here. The formula for standard deviation is not very attractive to those of you that are just now learning what some of these symbols might mean. You'll remember that X bar represents the mean, and it's the mean of a sample set. S, of course, since this is the formula for standard deviation, S is the same as standard deviation. Okay, I'll just abbreviate it like that, but S is the symbol that we use for that. X bar, of course, is mean, and we've always said that N is equal to the number of items in our set. And you may remember that the symbol sigma means that we are going to get the sum of all items. Okay, so according to this formula, as we read it, and I'll get some of this stuff out of the way, as we read it, this part is saying we're going to first off subtract every individual x from the mean, or subtract the mean from that value. We'll square those values, and then we will take the sum, based on this symbol here, we will take the sum of all of those differences that we get from every item minus the mean squared. And we'll talk about why we square it here in just a moment, but once we get that value, we're going to divide it by the number of items minus 1. And that's a long, lengthy discussion that I'm not going to get into in this lesson. We will talk about it eventually as we progress through this topic, but once we divide by n minus 1, we're going to take the square root of our answer, and that will produce the standard deviation for us. And again, that is a measure of how spread out the items are within a set of data. So, as confusing as that might sound, it's actually a fairly simple process. We're just going to find the mean, we're going to subtract everything, or the mean from everything, square those values, and divide by n minus 1 into the sum of all those values. So it's not as quite of a complicated process as the formula may look like. At this point, at this point, the formula is looking a little funny for us because we're just not used to a lot of these symbols that we're seeing here. But we will continue to work with these symbols, and you'll become accustomed to it. That said, let's look at an example where we begin to look at how to compute the standard deviation by hand. In this example, we're seeing Big Blossom Greenhouse. It's been commissioned to develop an extra large rose for the Rose Bowl Parade. If you've ever seen the Rose Bowl Parade, they make these elaborate floats that are decorated with roses all over them. And this greenhouse has been commissioned to develop a new type of rose for the Rose Bowl Parade floats. A random sample of blossoms from Hybrid A, one of its hybrid blossoms that it's making. they took a random sample of those and it yielded the diameters in inches here for mature peak blossoms. I'm having a hard time talking this evening. But we've been asked to find the mean and the standard deviation of the sample of roses. So first off, we're always going to have to find the mean first. So remember, we looked at the formula the other day that x bar, which stands for mean, is equal to the sum of all of the x's divided by n. And in this case, that means that we're just going to add up 2, 3, 4, 5, 6, 8, 10, and 10. And since that's 8 numbers, we would divide them by 8. Well, take a moment and see what you can do with that. Okay, so we can see that 2 plus 3 plus 4 plus 5, let's see, that's 5, 9, 5 again would be 14, 20, 28, 38, 48. So we get a sum of 48, and we're going to divide that by n. N was 8. So this works out really nicely to give us a mean of 6. Now what that means, no pun intended, is that x bar, our mean, is 6 inches. And the average rose of hybrid A, average blossom of hybrid A roses, is going to have a diameter of 6 inches. Now, what we're going to do now is compare each of these individual values that we have to this 6 inches and see how far each one of them is away. Are they all really close? In other words, are they really consistently going to be around 6 inches, or are they, real variable? Is there a lot of variation from item to item or rosebud to rosebud as we go through the set? And we're going to do that by measuring the standard deviation. So I've set up this little table for you here on the next page, and this will help you as we calculate the standard deviation by hand. You'll see that I've taken each of the individual measurements that we had and placed them in this column X. And you can see that I have all of the values here under this X are the actual measurements that we took of each individual rosebud. So what I have in this next column is each item subtracted with the mean. So each column minus the mean. We'll remember in the last frame we decided that x bar was equal to 6. That's our mean of 6 inches. So what we're going to do is we're going to say 2 minus 6, which of course is negative 4. We're going to say 3 minus 6, which is negative 3. We'll say 4 minus 6, which of course is, what's that, negative 2. And then you've got 5 minus 6 equals negative 1. And 6 minus 6 is equal to 0. And 8 minus 6 is equal to, what, 2? And of course 10 minus 6 is equal to 4. And 10 minus 6 again is still going to be equal to 4. Now, if we were to take a moment and get the sum of these numbers, in other words, you said we're going to find the average distance that every item is from X, and by subtracting, we found how far every item was from X bar, the mean. And when we take these items, there's an issue if we take the total of them, like we were going to try and average them out. So if we were to do that and we added them together, we would get negative 4 plus negative 3 plus negative 2 plus negative 1. I believe that's negative 10. Plus 0 is still negative 10. Plus 2 would be negative 8. Plus 4 and plus 4 would make positive, or would make another positive 8 plus the negative 8. That would make a total of 0. Excuse me, I'm getting tangled up in my words. But we got a total of 0 from all those values. So because they all add up to be 0, due to the fact that some are negative and some are positive values, we can't really find the average of those numbers. If we were to add them all up, the average would always be 0. So what we have to do is incorporate something else in to take care of those negative signs in order to get values that will not cancel each other out when we add them together. So what we'll do is we'll take each of these values and square them. as we square them, you'll remember that when we square a negative value, it automatically becomes positive. And of course, when we square a positive value, it remains positive. So as we square these, let's go through real quickly. Negative 4 squared is 16. Negative 3 squared is 9. Negative 2 squared is 4. Negative 1 squared is 1. Of course, 0 squared is 0. 2 squared is 4. 4 squared is 16. And again, 4 squared is 16. So now we have numbers that we can actually add together and work with without the fear of them canceling each other out. So as we add these up, we have 32. 16 plus 16 is 32. Plus 4 is 36. 0 and 1 would make 37. Plus 4 is 41. 50, 66 is what we get for our total there. Now this is the actual value that we're going to use. This is equal to that part of the equation that was the summation of x minus x bar squareds. And that's what we're actually using here. So we're going to compute the standard deviation using this value. Now again, we'll go back to the actual formula here. And we will use S is equal to the square root of the sum of x minus x bar squared, and we just found that value, divided by n minus 1. Okay, so let's take a look at what we have. S is equal to, we said the sum of x minus x bar squared is going to be 66. So we've got the square root of 66 over n minus 1. Now n minus 1 represents the number of items subtracted 1. So we've got 1, 2, 3, 4, 5, 6, 7, 8 items in the list. So we say 8 minus 1, and that gives us a value of 7 to divide by. And with some calculations, we will find that 66 over 7 is around 9.428, something or other, which is fine. We'll use that and take the square root. So the square root of that is going to be, tell us that S is approximately 3.07. So our standard deviation is 3.07 or 3.1 if you want to just use our rule for rounding there. And that's it. We've computed the standard deviation of 3.07. Our mean was 6 inches. So we can go back and actually answer the question that we had. The mean was 6 inches and the standard deviation was 3.07 inches. Now, what does that mean? Well, it actually means that on average, every number in that set was a distance of 3.07 inches away from the mean. Now, some of them were closer than that to 6 inches. Some of them were further away than 6 inches. But what we're saying is, on average, the items in that set of data were 3.07 inches away from that mean of 6 inches. And, you know, as you've been able to look at things, that might be considered kind of a lot of variation there. Let's look at another example here, and we'll go through the same process again just to get a little more extra practice. Now we're seeing that Big Blossom Greenhouse has another hybrid that they're calling hybrid B, and they've got a sample of those rosebuds or rose blossoms, and they've taken the widths of them. Now, we've been asked again to find the mean and standard deviation of hybrid B. And once we do this, we'll compare the two. And looking at this, real quickly, we add up the values because the first thing we want to do is find the mean. So the mean is going to equal the sum of all of these values, 5, 5, 5, 6, 6, 6. I believe that adds up to 33, plus 7 is 40, plus 8 is 48. So we have a sum of 48 that we're going to divide by the 8 blossoms that we have. And again, that gives us a mean of 6 inches. So rather curious that we have the same exact, we have the same exact value for our mean of hybrid B as we do for hybrid A. So one that was uneducated might think right off the bat that these two roses are exactly the same, since they have the same mean diameter. However, if we look a little closer at the numbers, we might pick up on the fact that something is up. Maybe one is a little bit different in variation than the other one. This one appears to be maybe a little bit more consistent. So what we're going to do is we're going to get a measure of the standard deviation and compare it. As we look at the standard deviation, again, we're going to take all of these items, the individual measurements, I've already laid them out here for you, and we're going to subtract each of those from the mean. And I'll give you a second to do that. Okay, and you can see I've gone ahead and done that for you. And once again, we have a list of items subtracted from the mean: -1 plus -1 plus -1 plus 0, 0, 0, and 1 and 2 all add up to be 0. So you'll notice it's not coincidence that the last one had a total of 0. Every time we do this, by the nature of the value of the mean, since it's kind of equally on one, or equally treated on one side or the other of it, it's going to end up giving us a total of 0 anytime we do this. So because of that, we're going to square the values so they don't cancel each other out. And again, -1 squared is 1. -1 squared is 1. This one will also be 1. That's -1 squared. 0 squared is equal to 0. This would be 0. This would be 0. 1 squared is equal to 1. So there we go with that again. And 2 squared is equal to 4. So now we have 1, 1, 1, 0, 0, 0, 1, and 4 that we can add up. And you can probably see this one's going to be a little bit different. 4 plus 1 is 5, 6, 7, 8. So we have a total of 8. So we go back to our formula. S is equal to the sum of x minus x bar squared divided by n minus 1. We've got our x minus x bar squareds right here, and we've already totaled them up. So they have a total of 8. So we'll go S is equal to 8 divided by 8 minus 1, which of course is 7. And 8 divided by 7, that's going to be somewhere around 1.14286, I believe, something like that. So when we take that square root, we're going to get something that tells us that S is approximately 1.07 inches. So we're now asked to compare the two types of hybrid roses that the Big Blossom greenhouse produced. Well, if we look at these, we had hybrid A, and we had hybrid B, hybrid A had a mean of 6, hybrid B had a mean of 6 inches, that is. Guess I should label that. But when we compared the two in terms of their standard deviations, they were quite a bit different. As we saw just now, hybrid B had a standard deviation of 1.07 inches. And we could see that hybrid A had a standard deviation of, what was it, 3.01? Am I correct on that? No, it was 3.07. Sorry about that. 3.07 inches. So we see that this one has a lot more variability than this one. And if we look back at the sets of data, looking at this set, the mean was 6, and we see that most of the blossoms had diameters that were very close to 6. We had several 5s, several of them even came out to be equal to 6, and one or two were a little bit larger than that, but for the most part, they were very close to that value. And that's why we got this standard deviation to be a lot smaller in this case. So if we look back at the original ones, or not the original, but hybrid A values, the mean was 6, but you can see only one value came out to be equal to that, and several others were, 2 and 3 were quite considerably off, and 10 down here, quite considerably off from the 6 inches that we had. So those values were a lot more spread out in value than the values that we got for hybrid B. So the question here would be, in this problem, if we were going to compare these two, which would we prefer? Would we prefer the one that was more consistently one size or very close to the mean, or we can prefer the one that got really big and then sometimes really small? Well, that's pretty much it. You've pretty much got the basics of finding standard deviation on your own by hand. We're going to look at some other examples later on in class, and we're going to try some on our own in our assignment tonight. So hopefully you're getting this, and if you have some questions, make sure you talk to me in the middle of class, and we can discuss any issues that you may be having.